Hey 13DPs, welcome back. This lesson is 16.2 on activation energy. Okay, so the essential idea is that activation energy can be determined from the effect of temperature on the reaction rate. Now, I'm not going to go through all of the understandings because they don't make any sense until you've learned them, but you can go back and tick them off when you can, when you know what to do. Okay. So guys, let's just jump straight into it. The first thing that you really need to understand is that the rate constant, which is this part here, is affected by temperature, which means it'll go up and down depending on temperature. Now actually you do know this because after we've created, we've spent some time learning how to do the rate expressions, there's some things that you know from prior knowledge. So you know that if we increase the temperature of a reaction, the rate of the reaction goes up because there'll be more successful collisions and more of the collisions will have the required activation energy. So we know that from our topic 6, the standard level section. Okay, so we know that point. And so we know that temperature has an effect on reaction rate. We also know that when we increase the temperature of a reaction, do we change the concentration of the species that are in it? And the answer is no, and we know that. So if we know that the rate goes up or down, so changes, but when temperature changes, but we know that these concentrations don't change, then the only thing that we're left with is K. So therefore, we can apply some of the things that we've previously known to this situation, and we can now conclude that rate constant is temperature dependent, which means it'll change with temperature. So rate of reaction depends on two things. It's going to depend on this K, and it's going to, this is the rate of a reaction, by the way, it's going to depend on the concentration of reactants raised to a power. So we also know that rate is determined by K, and the concentration of the reactants to a power. So therefore, the last thing is that we now know is that this K, the rate constant, depends on T, the temperature. So increasing the temperature increases the rate constant, which is really, really important. And the next thing is about activation energy. This whole section is about activation energy. So if we increase the temperature, does activation energy go up? And the answer is no, of course not. But what does happen is the number of successful collisions goes up, and therefore more collisions are successful. So activation energy itself is not affected by temperature, but there is some relationship between temperature and activation energy, and that's what we need to discuss. But really key thing is that activation energy will not change with temperature, okay? So just a bit of a real life connection here is the fact that wasps are only ever active in the warmer months. And the reason why is because their flight is dependent on energy which gets released in chemical reactions in their cells. And so at cool temperatures, the rate of those chemical reactions slows down, which is pretty cool. And that's the same as with flies. And that's why with flies, they're much easier to catch on a cold day than on a hot day. They're really buzzy and quick. Okay. So what is this relationship between activation energy and temperature? So you guys have seen this before, the Boltzmann curve, and you have to be able to do this. And so I'm going to do a little bit of a recap on the Boltzmann curve here. So this is the Boltzmann curve at two different temperatures, but the EA is consistent. Remember, if the temperature is changed, the EA remains the same. Okay, but more collisions are now successful. And so what you have to realize is that at a higher temperature, which is this bottom graph here in blue, is that the hump must be lower than the original hump and it must be moved to the right. And the reason for that is area under the curve is the number of particles. And so the number of particles will still be the same even if you heat up the reaction. And so you have to get those two things correct. And then you must show, so the hump must be lower, it must be shifted to the right. And so therefore that makes more of the particles, this area greater here. So that's kind of how that's marked. It's always a 2 marker, that one. So just looking at this graph here, there's a couple of things that you need to consider, and that's the level where EA is at. So in this example here, EA is reasonably to the right here, which means that the activation energy is high. So if the activation energy is high and we increase the temperature, so we go from T1, lower temperature, to T2, you get a massive change in the number of successful collisions. So here in a T1, that was the number, whatever number that is, and then it doubles, which is a big change when we increase the temperature, and that's because the activation energy was reasonably high to begin with. But what if the activation energy was down here, so reasonably low? So if the activation energy was reasonably low, the difference between T1 and T2 would be almost minimal, okay? And so therefore the starting activation energy affects how much of an impact that temperature will have. Okay, so the temperature dependence of K depends on the value of EA, because if the value of EA is high, it has a big impact. If the value of EA is low, it has a little impact. Hopefully that makes sense, and this graph kind of shows it. Okay, a probably better place for me to have put that to make it show a bit better would have been here, but whatever, down here. So yeah, you get the gist. Okay, so far these are the points that we know. We know that rate is determined by the rate constant and the concentration of your reactants raised to a power. So we know that that was our rate expression, that was 16.1. We also know that temperature will affect the rate constant, and we know that because concentration won't change with temperature, and we know rate changes with temperature. So therefore the only thing left is the rate constant. And the final thing is that we know that temperature doesn't change the activation energy value, but the EA's value will determine the impact that temperature has. So there has to be some way of mathematically expressing all these factors together. And there is. And the answer is the Arrhenius equation, which is given to you in your resource book. Okay? So we can look at this equation and and work out the rate constant from this equation, pretty much. So what we say is that the fraction of molecules which have the energy greater than EA, so they can have a successful collision at a certain temperature, is proportional to this. Okay, so E to the power of negative activation energy over RT, where R is the gas constant given in your book and T is the absolute temperature. So what they're saying here is we can use this expression to work out our rate constant, and this is how they're intertwined. And you don't need to work out how this is derived. So therefore, yeah, that's the key thing. Now, sometimes you'll see it expressed as this with an A in front. A is the Arrhenius constant. Okay, now that takes into account the number of successful collisions with the correct geometry and activation energy. It's a constant for a reaction, and it has the same units as K, which will depend on the order of that substance. But often you'll just see this is what we need to deal with. But please be mindful, sometimes that constant will be in there, and you'll see how we do the problems in a second. Okay, so there are two ways to calculate EA, and your exam could ask you either of these. So one is using a graph where you log the rate constant versus absolute temperature, okay? And then the second is if they just give you two rate constants and two temperatures, you can just plug it into this, which is given in your data booklet, but I'll go into detail. So just a reminder about a straight line in a straight line equation. So y equals mx plus c. Y is your y-intercept. M is your gradient. Y is your y-intercept. Y is your value here. Okay. M is your gradient. X is from here, and C is your y-intercept. So what we can do here is if someone does a graph for us, which they've done here, of the log of your rate constant versus the log of T, we just use logs to get better numbers, then what we can do is if we have this equation here, okay, and we take the log of each side, that would be log K, okay, by negative EA plus log A. So that's if you took the natural log of this, then this is what you get. You don't have to learn how to derive this. You just need to use this. It's in your data booklet. So we can actually use this. It's actually the same format as your straight line equation, where y equals ln k, okay, where the gradient is negative EA over R. Okay, so the gradient is negative EA over R, okay. X is 1 over t. Yep, there's your x, okay, and also log k, that was the y, so just putting those into perspective. And then your y-intercept is going to be log a, okay. So hopefully you can see how we've got that equation derived, okay, so it matches. So then what you can actually do then is you can, if you have a graph of log rate constant and over log absolute temperature, and then you can actually take the gradient of the line, and the gradient of the line will then tell you the activation energy. So because if the gradient is negative EA over R, okay, then and we know R is a rate constant, okay, then we can rearrange, and your activation energy will be your gradient times the rate constant. Okay, and that's really important. So we can do the gradient of the line, rearrange with R, and it'll solve for your activation energy, which is the whole point here. So we can see what the activation energy of a reaction actually is, which is pretty cool. Just a reminder that temperature won't change the activation energy, but the rate constant does change. So here's some data, and I'm not going to get you to plot it, I'm just going to show you. So various rate constants at various temperatures is what that data is. And so this is a kind of an example question you could get, and it says determine the activation energy using graphical method. So graphical method means you have to take the log of your rate constant versus the log of your absolute temperature. And you can see here it's a -1, and so we've got a negative gradient. So to do the gradient here, you'd take 2 points and do rise over run, and you'd make them as big as possible if you can when you're doing the gradient. So if we've got the gradient, which we've got, and we know that the gradient is negative EA over R from that straight line equation, that means that we can take the gradient, times it by the R, and we will get our EA. And because the gradient's negative and R is a positive, negative times a positive, and then we divide by the negatives, our EA will end up being positive. And you can see we can rearrange, and that's how you can get your EA. Okay, so it's not too challenging. Yeah. So the second way of calculating EA is if they give you 2 rate constants and 2 temperatures. This comes up probably more frequently, I would say. And so you can use this equation here. So this is taking the log of each side at 2 different temperatures, T1 and T2, and then they're combined here, and you get this lovely combined equation in your data booklet, which is perfect, and all you have to do is plug them in. It's that simple. So here's 2 rate constants, here's 2 temperatures. Remember, temperatures must be in Kelvin. Okay, so here's our temperatures in Kelvin. Okay, here's our rates 1 and 2. Just make sure, the biggest mistake kids make is they put them round the wrong way. They don't pay enough attention. Okay, and EA is what we're solving for. R is a constant. You were given these, and so you just plug them all in. Please, can you chuck this into your calculator now and check you get that answer? There seems to be a lot of issues with being able to use log. So please make sure you can chuck that in and you get the same answer. And if you're having any issues, let me know on Teams. But that's the second method. So it's not too complicated. It's just recognizing, first of all, with the first method, that gradient is negative EA over R. Okay, negative EA over R, and R is the gas constant. And the second method is just using this expression here, and you'll be given 2 data points. And that's it. The final thing for this section is what happens if we add a catalyst. Well, we know that adding a catalyst speeds up the rate of the reaction, and the reason why is because more particles have the required activation energy. The activation energy hasn't been altered, so therefore what has changed? If the rate's going up, and it must be the rate constant, because if the activation energy itself is staying the same, that's what it has to be. So here are 3 summaries. If temp changes, the rate constant changes. If temp changes, EA stays the same. And if a catalyst is added, the rate constant goes up. please complete these questions. That's all for activation energy.